Chapter 4 addresses the forward kinematics of open-chain robots, as illustrated in this video of a robot with 6 revolute joints. We define a frame S fixed in space, often at the base of the robot, and a frame B at the end effector of the robot arm. If we command the robot to move, the B frame moves. The forward kinematics problem is to find the configuration of the B frame relative to the S frame, given the vector of joint angles theta. The transformation matrix representing the B frame and the S frame is TSB of theta, or just T of theta for short. To derive a procedure to calculate T of theta, let's use a simple robot arm that moves in a plane. This robot has 3 joints: a revolute joint, a prismatic joint, and another revolute joint. You can also see the stationary S frame and the end effector B frame. This is a stick figure version of the robot. The joint variable theta1 represents the angle of joint 1 relative to the horizontal. Theta2 represents the extension of the prismatic joint, and theta3 represents the angle of joint 3. The 3-vector theta is a list of 3 joint variables, and T of theta represents the configuration of the B frame relative to the S frame. If we set all of the joint variables equal to 0, the robot is in its home position as shown here. We write the 0 configuration of the B frame as T of 0, or simply M for short. At the 0 configuration, the B frame has the same orientation as the S frame, and the 3 in the top right element of the M matrix means that the B frame is 3 units from the S frame in the XS direction. Now say we rotate joint 3 by pi over 4 radians. The theta vector is now 0, 0, pi over 4. This motion of the B frame can be represented by a rotation about the screw axis of joint 3. Since it is a revolute joint with no translational motion, the screw axis has 0 pitch. Because positive rotation is in the direction indicated in the figure, by the right-hand rule, the screw axis is out of the screen, toward you. As we learned in Chapter 3 videos, the screw axis can be represented in any frame. Let's represent it in the S frame, and let's call joint 3's screw axis S3, consisting of an angular component omega 3 and a linear component V3. Since the screw axis involves rotation, omega 3 must be a unit vector. Positive rotation is about an axis out of the screen, which is aligned with the S frame's z-axis. Therefore, the unit angular component is 0, 0, 1, a unit vector aligned with the zs axis. To visualize the linear component V3, imagine the entire space rotating about joint 3, visualized here as a turntable. Then V3 is the linear velocity of a point at the origin of the S frame when the turntable rotates with unit angular velocity, as shown here. So V3 is 0, minus 2, 0, meaning that the origin has a velocity of 2 units in the minus ys direction. V3 could also be calculated as minus omega 3 cross Q3, where Q3 is any point on the joint axis represented in the S frame. Now that we have the screw axis S3, we can calculate the B frame configuration T of theta. We simply apply the space frame transformation corresponding to motion along the S3 screw axis by an angle pi over 4. This transformation is e to the bracket S3 times pi over 4 using the matrix exponential from the Chapter 3 videos. Since it is a space frame transformation, it pre-multiplies m. Now suppose we change joint 2, extending it by 0.5 units of distance. The theta vector is now 0, 0.5, pi over 4. The screw axis S2 corresponding to joint 2 has 0 angular component, omega 2, so the linear component V2 must be a unit vector. If we imagine the whole space translating at unit velocity along joint 2, a point at the origin of the S frame would move with a linear velocity V2 equal to 1, 0, 0, expressed in the S frame. Therefore, the screw axis S2 is defined as 0, 0, 0, 1, 0, 0. The new configuration of the B frame, T of theta, is obtained by left multiplying the previous configuration by e to the bracket S2 times theta 2. It's important to notice that the previous motion of joint 3 does not affect the relationship of joint 2's screw axis to the S frame. That's because joint 3 is not between joint 2 and the S frame. Therefore, S2 is the same as the screw axis of joint 2 when the robot is at its 0 configuration. Finally, let's rotate joint 1 by pi over 6. The theta vector is now pi over 6, 0.5, pi over 4. The screw axis S1 is a pure rotation about an axis out of the screen, so the omega 1 vector is 0, 0, 1. Rotation about this axis does not cause any linear motion at the origin of the S frame, so the V1 vector is 0, 0, 0. The new configuration of the B frame, t of theta, is again given by left multiplying the previous configuration by the new space frame transformation. Again, the previous motions of joints 2 and 3 do not affect the relationship of joint 1's screw axis to the S frame because they're not in between joint 1 and the S frame. Therefore, S1 is the same as the screw axis of joint 1 when the robot is at its 0 configuration. For any serial robot, the procedure generalizes directly. First, define the M matrix representing the B frame when the joint variables are 0. Second, define the S frame screw axes S1 to Sn for each of the n joint axes when the joint variables are 0. Finally, for the given joint values, evaluate the product of exponentials formula in the space frame. In the next video, we'll see an alternative version of this formula in terms of screw axes expressed in the B frame.